Okay, thank you, Mrs. So I'm Deconinck, and I will present you the recent results from a project together with VTP, the Technical Research Center from Finland, and it was funded by the European Offer project, and we investigated the interaction between hydrogen and laser powder bed fused made by or post-processed by different post-processing treatments. So I'll quickly go through the background, then I'll go into the results with the interaction between hydrogen and the material, and then I'll give already the conclusion that it really depends on the microstructure, how it is behaving. So first, why did we choose this material? We all know that 316L has a very good resistance against corrosion, also at higher temperatures, and it also has very good mechanical properties. We know for conventionally manufactured 316L, the interaction with hydrogen, so it might reduce the stacking fault energy, it might form Martensite, but this new type of manufacturing, the question is how is hydrogen behaving now in this alloy? And there are some literature papers known that the laser powder bed condition has equal or better resistance to hydrogen compared to the conventionally manufactured 316L, although actually industry is rather interested in post-processed 316L because it reduces the stacking fault, it reduces all the defects that are formed during the production, and it optimizes the mechanical properties. So here it is the evolution. If we increase the post-treatment, first only stress relief, we see still the microstructure that is present after additive manufacturing, which the grains start to rearrange when we also apply an annealing treatment at higher temperature. And we see that the grains are almost fully rearranged to an equiaxed structure with some twins present as well after the hot isostatic pressing at high temperature as well as high pressure. It's worth to note that this structure is actually quite similar to the conventionally rod structure, also rather equiaxed grains and also some twins that are present. So we decided to focus on those two post-treatments. On the one hand, stress relieved condition, on the other hand, the hot isostatic pressed condition, because both on the micro level as well on the nano level, they have a different microstructure. So we see in the stress relieved condition that there are still a lot of dislocation cells present. They were not resolved after the stress relief heat treatment at medium temperature, whereas they all are almost totally resolved after the hot isostatic pressing condition. So first of all, the hydrogen charging conditions, we always did galvanostatic charging at 60 degrees in the phosphoric acid with glycerol solution. And we see that the stress relief condition takes up definitely more hydrogen compared to the HIP condition. Although we should take into account that in this case, the sample is not fully saturated yet, but the main reasons that we see this trend is on the one hand that there are more grain boundaries present in the stress relief condition, but then secondly also these dislocation cells play a role because they serve as a kind of a hydrogen highway to promote the hydrogen uptake and transport. Then we went to the mechanical testing. Well, it's quite what we expected. This is for the stress relief condition. On top, you see the air condition. On the bottom, you see the hydrogen condition. And yeah, as we expected, the hydrogen condition fails earlier, and you also see some cracks present on the fracture plane. The same holds true for the HIP condition. Again, here there are even more cracks on the fracture plane, on the normal plane here, and it fails earlier as well compared to the HIP condition, to the air condition. The mechanical curves reflect what we saw earlier, but first I want to point out the difference between air stress relieved and the hot isostatic rest condition, because the stress relieved condition, it has a higher strength and also a lower elongation and fracture, but still it is quite ductile for both conditions. So when we then add the hydrogen condition, we see something interesting. Well, hydrogen embrittles the material, but to a lower extent in the stress relieved condition, only 13% in the stress relieved condition and 31% in the hot isostatic pressed condition. Although I should note, like, the absolute value is both around 0.6 engineering strain where it fails. Apart from this embrittlement effect, we also see a hydrogen-induced hardening. Well, very low amount for the stress relief condition, but quite a significant amount for the hot isostatic pressed condition. So we were looking further, where does this come from? First, in the fractography, well, what do we see? Yeah, in both cases in air, there are a lot of slip lines, no cracks present. On the other hand, in the hydrogen case, we see many secondary cracks present. The crack density is even higher in the HIP condition. Well, similar or expected results are on the plane. We see the voids present in the air condition. The void size can be related in the stress relieved condition to the dislocation cell size that we saw earlier. So that's why the void size in SR is lower than in HIP. And then when we go to the hydrogen condition, we got more brittle features with some quasi-cleavage features in both cases. So yeah, it looks quite different. So there was something else that was causing this difference in the effect. So we did XRD, and yeah, of course, we compared three conditions. On one hand, first the one in air, then with hydrogen charging before the tensile testing, and then with hydrogen charging after 25% straining. We see mainly there's austenite present. The peak becomes broader, which is expected because hydrogen is inducing strain, and then the deformation will also even more broaden the peaks here. But interesting here is that in the case of HIP, after deformation, we see some epsilon martensite present. And this observation was also confirmed by EBSD, that there is epsilon martensite present. I just want to remember you that actually this microstructure is quite close to the conventionally wrought microstructure, where we also saw, or where we know there can also be martensite forming. We only saw epsilon martensite by this technique, but we went even further to it. We took a lamella from the fracture plane. Well, this is on top is parallel to the normal plane. This is a crack tip that was present. And let's say around, there was all austenite present, but we took a diffraction pattern right in the middle. And there we saw it was epsilon present, epsilon martensite. And taking the dark field again, we see that epsilon is actually present along the crack. So the crack is propagating along this epsilon, or yeah, epsilon is promoting the crack propagation. Here we also see a specific feature, some kind of stress intensity field. And yeah, we see here both a combination of epsilon martensite and also alpha martensite. Looking further into the dark field, it's like the center is completely alpha, and then around we have some epsilon that is present there. On the other hand, so So far, this was for the hip condition. We checked in the stress relief condition whether or not there was this epsilon marten or alpha martensite present, but we could not find any. We saw here a lot of defects.
2 minutes.
Right. This one, for example, well, no, the defects, you see the dislocation cells that are disrupted. You see nicely aligned dislocation lines, slip bands, but then also some stacking faults like here, and also the parallelogrammic structure here, which we took then other diffraction patterns, only the austenite presence, but like there is a difference between, for example, this line and without this line. In this line, we see here, like, okay, maybe it's not very well visible, but there is kind of a line in between which indicates that there are more stacking faults, which is, yeah, probably introduced by hydrogen, but this stress relief structure still has a good resistance against this, this hydrogen effects. So it brings me to the conclusion that actually, depending on the post-processing, you can really tune between either a good hydrogen embrittlement resistance or mechanical properties that you want. And then in this example, the stress relief condition has a higher strength and better hydrogen embrittlement resistance against. All right. So thank you for your attention.